Right, hi. So my name is Aizan. I am a part of the Aspect Berkelanjutan group, and sorry for the environment, but I have to do something else for now. I will be presenting about the usage of electric scooters inside of ITB Indonesia, and yeah. So the main reason why we choose this topic is that ITB Indonesia covers a large area which students and faculty members would find hard to traverse in a short amount of time because of the big size and our strict policy on late. So we chose this because of that. And let me hold on for a second. I'll go for this project. Okay, so as I was saying, our goal for this project is to research and develop designs of the scooters and determine how effective it is if it's being implemented in campus. So I'm gonna pass off the next topic onto my friend here.
SDG or Sustainability Development Goals are essential to manifest our proposal success on whether or not an electric scooter is viable on ITB campus. The following SDGs that are related are the following. The third SDG being good health and well-being. Why? Having an electric scooter will make transportation less tiring, more personalized, and lowering the stress of being late as you have a quick vehicle to travel around with. Then the 11th SDGs being sustainable cities and communities. Why? Electric scooters do not produce gas emission as they are electrically powered. This promotes a green environment which also fits with ITB motto to build a green environment that are safe and sustainable. Then the 17th SDG, which is partnership for the goals. Why? Electric scooters aren't cheap. So communication, partnership, and design cooperation with teaching faculties as a research opportunity and available local companies that can provide will boost partnership to achieve such goals.
All right, so right now we will discuss about the calculation. So firstly, we start with a slender bar that is simply supported at A and point B with a distributed load of P of Newton per meter. Now we will do the section diagram to obtain the moment diagram, and here we can calculate the bending stress, right? Now, as you can see, this is the maximum bending stress, which will get the formula, which is positive for tension and negative for compression. And we'll try to find the material index using the strength to weight ratio. So now I use the mass formula, which is rho times the volume. The volume is width times height times length with a constraint variable of here. Now here, I'll just relate the bending stress in respect to its geometry and then plug in the formula to get the material index of the strength to weight ratio. Now I will want to also calculate the material index for the beam deflection. So the beam deflection, you can use the things that we have learned in solid mechanics. So we'll use the deflection formula and we can calculate the maximum deflection here. And as you can see, we can get the material index by relating the deflection to its geometric parameters, which we plug into the mass, which will take the inverse of it. The reciprocal of it to get the material index. Now this one will be a bit difficult. We will try to find the material index of torsion. So here we will use what you call the Saint-Venant's theorem. So the Saint-Venant's theorem stated that a body at deformation is governed by a contour-like graph called stress functions. Stress functions are scalar function, meaning that it does not really have a direction. However, it does have magnitude. So now, since we don't really have an established data, a textbook established data for non-circular geometries, we will have to derive it our own. Right? So we use the Poisson equation of the Saint-Venant's theorem, and then we use the finite Fourier sine transform. You can use the finite Fourier cosine. You can also use the superposition method, or you can also use since this is practically the Poisson, and Poisson is a subset of Laplace, you can also use the green function formula not formula, I'm sorry, green function method. However, the simplest one is the finite Fourier sine, which I take the finite Fourier sine and take one and plug it in back to the formula here to get an algebraic equation. And once you're done with that, you get the equation in terms of the finite sine of u, and then we take the inverse finite sine to get u back, right? So here we'll get the u as a function of x and y because it is independent of time. So we'll then plug it in to get the stress function formula, which we'll get, as you can see, this is sinusoidal. So how is it sinusoidal, right? Isn't stress function should be circular or perhaps rectangular? Well, keep in mind, according to Fourier series, any function, whether it's a square, it's an impulse, or it's a circle, can be represented by a sinusoidal graph. So that's what we do, and I use a small angle approximation. I assume that as the stress function approaches the edges, it will become more alike to the geometry. So that means, according to a small angle approximation, which I plug in here and derive, I'll get this. And we know that theta is approaching 0, so this is practically 0, right? And we know that as theta approaches 0, cos theta approaches 1. So now I'm only left with this stress function, right? And then now I can plug it in to the formula to find the torsion. Now, this is the simplified model where h is far less smaller than L. However, for a more realistic case, this is it, which you can also get the material index from here. Alright? Now, however, there is a very big problem for this one. The error, if you calculate it, which I will show you next on the design option, it will exceed the 5% confidence level. So meaning that it will reject the acceptable confidence interval, which is not allowed in engineering. So that means we have to use another formula, which we have to search through textbook, which is the Rourke's formula. Rourke's formula, where b is the width and t is the thickness, which is the height. So now the error will be far more smaller and will be more realistic. Now I also calculate the material index for fracture, and here I calculate the flaw size. And this is the material index in relation to the density and the fracture toughness. Now I also calculated the vibration mode. Well, we calculated the vibration mode, which is the model. So here I assume that this is our slender beam that we calculated before for the material and so on. Now I added a torsional spring and a damper here. Now there is the spring and there's the damper for the wheel, and then there is the torsional damper and the spring. Now, as you can see, this is a 2 DOF. So we want to calculate the two types of modes, that is the bounce and the pitch. Now, since we don't really have the design constraint for the vibration parameters such as K and C, so we only derive up until we can get the characteristic polynomial to get the sigma, which is the exponential decay, and omega d, which is the damping frequency. Since we are dealing with damping, this is no longer a free vibration. Now there's also the brake design, which I just take straight from our design and manufacture 2 class. And F grip is the average grip of a human hand, which is around maybe 400 newtons ish. And R hydraulic is the radius of the hydraulic tube, because this is a disc brake, just like a bicycle. So this is the double integral and so on. Now there's also the bearing design. The bearing design, we use the SKF formula for reliability greater than 90%. Now, since there are no axial loading, we can find from the table on the book that x1 is equals to 1 and y is equals to 0, and you can just use the SKF catalog. Now for the design constraint, we decided several things. So firstly, there is the 125. What is this? This is the geometry of the slender bar. So the length is 100 centimeter, the width is 20 centimeter, and the height is 5 centimeter. The force load is around 3,000 Newton per meter. So why 3,000? Because we know that the human body will be around 80 kilograms. and multiply by 10, that would be around 800 kilograms. And you have to consider that students will carry a bag around 1 to 2 kilograms, so that's around 820 and until 810 to 820. However, that's a bit too strict because that means our safety factor will be around 1 and it could be lower, and we don't really want that, so we give it an overkill design around 3000. So now we calculate the maximum bending stress, which we got from the formulation below, which is around 9 MPa. Now we want to amplify this model because of course this is on static condition. What if it encounters a bump or an impulse, right? It crashed or something. So we have to define another factor. There is the dynamic load factor, or DLF, which is straightly obtained from the force vibration model. This is actually from the Laplace transform. So we calculate this is 1.084, which is, since this is steady state FRF, this is expected because this is our calculation is also for static and this is for static too, so it's not really significant. So the dynamic load factor becomes a static load factor actually, so it doesn't really amplify it that much. So we have to use another dynamic load factor, which is the impact loading. So the impact loading, where h is the height of the bump and delta is the deflection. So as you hit the bump, it will deflect, right, from the material properties, right? Well, if that deflection is really, really small relative to the bump, and the bump is also really small relative to the deflection, so it's approximately 1, and this will result in 1 plus the square root of 2, which is around 2.414. So multiply this by the stress, which is around 21.726 MPa. Now we will use the Ashby chart. So this is our calculated design constraint, 21.7826 operating maximum bending stress, and this is our maximum one, 400, because 400 MPa, which means that it will be very strong, and very strong material tends to be very expensive. So we had it here as our commercial design factor, and we want to ensure that it's not too light. Too light, it could be brittle material. So as you can see, as you go from this side of the material, it is brittle materials, wood and so on. We don't really want it to be brittle, we want it to be ductile, but too much of the density will become heavier, and higher density, higher weight, slower velocity, and we wouldn't reach a class on time. So we don't really want it to be that heavy, and it will be a burden to carry. So we'll calculate right in between, which will get this. And as you can see, it intersects the second line from the bottom, which intersects aluminum alloy. Or you can also use another design analysis, which is HS, which is high strength and high density. This is not really good. What we want is high strength and low density, and we know that the majority of the one covered here area is aluminum alloy. So which means we use aluminum alloy, which we use 6061 T6, which is the most common industrial aluminum alloy. Then for realistic glaze, as you can see, we calculated the error is more than 10%, more than 5%. So we use the Rourke's formula as a correction factor. As a correction value. So we plug into the torsion, and we will get the shear stress of the torsion, and then we use MSST for failure analysis. And as you can see, the safety factor due to shear is 603.23, which is very, very safe. Then we calculate the flow size, which is for our maximum flow size. Our maximum crack length is 0.567 meter, which is 56.7 centimeter, which is higher than the length of our height, right? Which is 5 centimeters. So which means that crack will not govern. It might occur, but it won't be significant. That's what it means. Now, if it is on maximum operating condition, which is 400 MPa, so it will be 1.67 millimeter. That is the flow size, very, very small. So if the crack length is 1.673 millimeter greater, so greater than that, so it will, brittle fracture will occur. So that is our calculation, and we will move on to the statistical analysis of the cost. Alright, now we will calculate the cost of all of this. Now, there are several components, which I get this from a research paper for electrical scooter. So this is not our model, this is someone else's model, which we got from ResearchGate. So this is the common electric scooter controller schematic circuit. So we calculated the components needed. So there are BLDC motor, which is a quantity of 2. Of course, there are 2 wheels. So there are 2 motors. It could be 3 if you want a 3-wheeled scooter. There is the control board here, the SLG 47115 V. There's the brake light, throttle, speed limiter, not limited, but speed limiter, because if it's going too fast, it should slow down. There's the FET driver, there's the PWM, LED strips, capacitor, per cap. Since the per cap means because it's sold in usually bundles, right? Disc brakes, and there's the total price. So the quantity you can see here, and then this is the price in USD, which I got it from Amazon. Of course, this is it could have been cheaper because if it's from Amazon, everything is tenfolds there. So that's why the price is highly expensive. However, if you use local markets, it will cut the cost by 30% or so. So this is the price in USD, the quantity, multiply it here, so you get the total price in USD, so around 318.98 for the control system alone, right? Now I want to add the cost of the aluminum. Now keep in mind, since our dimension is around 100 times 20, 100 times 20 times 5, so you multiply that. Well, this is right to the density of the material, which you'll get around 27 kilogram, right? Which you get 27 kilogram, and then you multiply this by the 3.5 is the cost index, which is 3.5 USD per kilogram. So you'll get the cost here, which is around which is around $94.5, right? Now I also added production cost. Production cost is around 2.5 USD per hour. So multiply that by 10 hours because it's 7 to 5 or 9 to 5 usually, right? Around 10 hours ish of work time. So multiply this by the current USD exchange with the fixed inflation and so on, which is you can find in Google, which is around 16793.49 IDR atau sekitar 17.000. So calculate all of this, which you'll get around 7.4 million USD. I'm sorry, IDR, Indonesian dollar, or that's equivalent to 438.48 USD. So it's quite expensive. So how do we reduce the cost? Well, of course, as I mentioned before, you can use local markets, and of course, partnership will reduce the cost significantly, such as communication between faculties, because of course this is the electro students part, while the material and motors and stuff are our stuff, right? Mechanical engineering aspect. So partnership and funds investment, it will cut the cost cheaper.